Welcome to the 23rd video of this course on quantum processing. This is the last video and I dedicated for the topological quantum mechanics problem that we will see connecting the Nobel Prize justification and the motivation for this last year's Nobel Prize in physics. So let's begin to think of the topological effects that we can think of. We have the integer quantum Hall effect, the Hall effect, the quantized Hall effect, and the fractional quantum Hall effect. So the integer quantum Hall effect was hugely studied by David Thouless. So and you have the fractional quantum Hall effect for many things related to Duncan Haldane, and topological insulators resulting from, if you know the spin-orbit coupling. But what we will focus on this video is the integer quantum Hall effect. So remember the Nobel Prize in physics last year for the phases of matter, the topological phases of matter, also the transition. And actually David Thouless shares half of the prize in this part and also in the other part. So let's begin to think of the language of the Berry physics, okay? So the Berry physics, if you have a wave function, okay, this wave function is psi, say for parameter r, vector r, and you evolve this wave function by the space evolution, you can see that it picks a phase shift. Okay, we know the phase shift from quantum mechanics as the dynamical phase. What we know in most of our study in quantum physics is this dynamical phase phi d. But actually we want to focus now on the Berry phase, the geometric phase. This Berry phase is the geometric phase that the wave function can evolve and pick during its journey around parameter r, for example, or area, whatever. So let me tell you about the span-Berry physics phase here quickly, that if you have this coherent state, okay, this coherent state is evolving, you see clearly here. Remember the Bloch sphere representation, this is a Bloch sphere and this is a spin, and this spin is rotating around an area here in around the z-axis, for example. Okay, so this is y and this is x. So we have a coherent state, okay, this coherent state is an eigenstate of the spin operator, okay. So it looks like this is spin coherent state, rotating a spin around this area. And actually you will see in a second that this term is nothing else than magnetic field. Okay, but let's just focus on this spin problem, that for Berry, we call it the spin-Berry phase, and the spin rotation around here, if you take the overlap of the whole spinners around each section, each subsection of the area corresponding to each spinner, and if you take the overlap, the inner product, the overlap of the spinners, you find it's equivalent to this exponential representing this important factor here. This factor of gamma is called the geometric phase. This is the geometric phase, and it represents the area of this part of the whole sphere here, the circumference here. This is called the geometric phase. So, and by the way, this expression here is called the Wilson expression, Wilson loop expression. So it's called Wilson loop if you take the whole this overlap of the spinners. So this exponential actually is about 2 pi, because the area of this circle is 2 pi. And if you take the spin s here and consider this exponential at the spin 1/2 system and a spin integer system and a spin half integer system. For a spin integer system, let's say plus or minus half. So plus or minus half is actually equivalent to e raised to I. And here I have 2. So it's here now 1. So it becomes here just, actually this is just 1 minus 1 here, related to, I'm sorry, just I wrote down this 2 pi, this minus 1 raised to the s, so the s of 2s here. So the s, if it's 1/2, actually you would pick the minus again, and if it's 1, so just 1 here, you pick the +1. So you see the distinction between both in the case of the spin 1/2 system and a spin integer system that you can see. So let me tell you that this is important to define the following parameters, okay, here. So let's consider some formalities of the Berry physics here for studying the evolution, the quantum evolution of a flux in a magnetic wave function in a flux or in a magnetic field. So the Berry phase, the Berry phi here, can be defined as you take the contour integral of the what we call here, this is called the Berry connection, but this is just nothing else. And if you invoke Stokes theorem, you can find that this is equivalent to taking the line integral around R. Here is parameter R. This is say R, and this expression is equivalent to take the contour integral of A is equivalent to take the line integral of the Stokes theorem here reveals that you take the curl of this A. This is what we call the Berry connection. Keep it for a second. You will see it now here. And this Berry connection, you take it around the S, the whole area. It's equivalent to the Berry phase expression here. So two important things here to see, that this A of our parameter R you evolve. This is considered to be an eigenstate of U of R, and you evolve that. So you take the overlap again with the eigenstate, and here just take the gradient with respect to R, and it's equivalent to what we call the Berry connection. This is the Berry connection, and here for what I said before, you just nothing else in the magnetic field. Actually, you take the curl of the Berry connection, you reveal what we call the Berry curvature. This can be a multi-dimensional parameter space, any parameter space you wish for this generalized curl that you take for the Berry connection.